Am I audible? Uh,
Yes, ma'am.
okay. Uh, then we are starting within 2 minutes. So, welcome everyone for the seventh problem solving session for the NPTEL course and Introduction to Climate Dynamics, Variability and Modeling. From this week onwards, we will see the main important aspect which shapes the Earth climate, that is, how the air parcel moves or how the ocean current flows. And we first want to know what forces shape the movement of this ocean currents and or the air parcels. So this first in the week 7 lecture, the movement of the air in Earth's atmosphere was covered. In this week 7 today's session, we will cover mainly the week 6 and the week 7 lecture problems. So also now you can unmute yourself or you can write the answer in the chat box. So this is the this is our first question. This first question up to 1 to 20, these questions are mainly from the week 6 content. So today's first question is, which of the following gases contributes significantly to the shortwave heating in stratosphere? Ozone, water vapor, carbon dioxide or nitrogen? Which of the following gases contributes significantly to the shortwave heating in stratosphere? Ozone, water vapor, carbon dioxide or nitrogen? Yes, ozone is the key thing which or the key gas which contributes to the shortwave heating, because ozone absorbs the shortwave radiation that is coming down from the top of atmosphere. Now the second question is, water vapor largely determines the lapse rate in troposphere. Is this statement true or false? Water vapor largely determines the lapse rate within the troposphere. Is this statement true or false? This water vapor is the main component which determines the adiabatic lapse rate. You know, in the troposphere the content of water vapor is high. So this question is true. This statement is true. Now, whether this third statement is true or false, shortwave radiation contributes to both heating and cooling of atmospheric layers. This statement is true or false? Here, the key thing they are mentioning, both cooling and heating is done by the shortwave radiation. Shortwave radiation contributes to both cooling and heating of troposphere layers. Whether this statement is true or false? Shortwave radiation only contributes to heating of atmosphere. It has no effect in cooling, because cooling of atmosphere is mainly done when some amount of some gas or molecules absorb the radiation or they emit. So this shortwave radiation is not absorbed by any of this in the molecules. So this the statement is false. Here only the true statement is shortwave radiation only contributes to the heating of the atmospheric layers. because the shortwave radiation cannot be absorbed by the atmospheric gases. In the question 4 is similar kind of true or false question. The shortwave hitting rest reaches peak at the optical depth 1. This statement is true or false? Yes. The shortwave hitting rate is maximum when the optical depth is 1, uh, because you can see that I is equals to e to the power minus I0 into e to the power minus tau. As the tau value is higher, then the heating is high, absorption is high, that means heating is high. So for this question there is ozone, then there is less determines the lapse rate in troposphere. This is true. Shortwave heating contributes both to cooling and heating of atmospheric layers. This is false. And question 4 is true. Now question 5. The net upward long-wave radiation at certain frequency has been given with a function here, that is Fz is equals to 2z square minus 50.
Excuse me, ma'am.
Yes.
Excuse me. The question is too small. It is not
Okay.
visible properly.
Is it now visible?
Yes, yes. Now
Okay. The net,
it's okay. It's okay.
yes. I will give some time, 1 minute, 2 minute time. The net upward long wave radiation at certain frequency is given by this formula, that is the Fz or Fz upper, that is equal to 2z square minus 15z plus 150 in the unit of watt per meter cube. Hertz, meter cube per hertz, because at certain frequency you can see that is F nu z, and z is given in the kilometer from the sea level. This volumetric heating rate value for the radiation at this frequency at 5 kilometer above the sea level is what? You have to mention this. Answer will be coming in unit of the watt meter cube per hertz. We know rho q dot, or the volumetric heating rate, is equals to minus del F nu del Z is equals to volumetric heating rate. in question 5, it is mentioned that the upward flux is equals to 2z square minus 15z plus 150 in the unit of watt per meter cube hertz. And this volumetric heating rate has been defined as minus del f del z. So if you just take the derivative of f with respect to z, then it comes the 4z minus 15, and here for del del z of 150 or constant is 0. So if you plug in the value z is equals to 5 kilometer, then it comes at minus 5 watt per meter cube hertz unit. So for the question 5, option D is correct. Have you got the value? Yes. Now question 6. What is the impact of carbon dioxide in the temperature profile at both troposphere and the stratosphere according to the radiative transfer model? So you have to first decide what before doing this question we will just say this understanding of this radiative transfer model, that this water vapor is the key thing which determines the lapse rate in the troposphere, and then for the carbon dioxide, for the stratosphere there is some increase of there is some shift of this line, and from the stratosphere this line for the O3 this line shifts more. Now you have to just we can revisit what is the impact of the carbon dioxide in the temperature profile at both the two lower layers, that are troposphere and the stratosphere, according to radiative transfer model. Option 1, carbon dioxide decreases temperature by 10 Kelvin in troposphere and increase it by 20 Kelvin in stratosphere. Increases temperature about 10 Kelvin in troposphere and decreases it by about 20 Kelvin in stratosphere. Increases temperature about 20 Kelvin in troposphere and decreases it by about 10 Kelvin in stratosphere. Decreases temperature about 20 Kelvin in troposphere but increases it by 10 Kelvin in stratosphere.
All are incorrect, I think.
Yes, I guess so. Decrease, increase, increase, decrease, increase, decrease, decrease, increase. Yes. So in the there is two in the two case there is increase of temperature. So here it is has been given that carbon dioxide at small bit but important correction of increasing temperature of 10 Kelvin in troposphere and increasing it about 20 Kelvin in stratosphere. So in the both these lower layers, that are the troposphere and the stratosphere, carbon dioxide is responsible for increasing temperature. In the troposphere it increases temperature at 10 Kelvin. You can see by the red line. It is more closer to H2O line, but in the stratosphere you can see there the shift is more here. So here the 20 Kelvin increases has been done by the carbon dioxide at, and here you can see in the troposphere the main increase is in the stratosphere the main shift has been done by the O3 or ozone. So for this question 6, all are incorrect. In the question 7, why the temperature lapse rate is found to be unconditionally unstable in the radiative equilibrium best temperature profile models? Due to neglect of the convection and the latent heat transfer, due to neglect of the short wave heating fluxes, due to rapid turning of the temperature profile because of presence of greenhouse gases. Why the temperature lapse rate is found to be unconditionally unstable in the radiative equilibrium best temperature profile models?
Option A.
Yes, the correct option is A. This unconditionally stable or unconditionally unstable is solely linked with the latent heat transfer and the convection. Uh, as this radiative equilibrium best temperature profile only takes care of the short wave heating fluxes thing and the temperature, how the temperature uh, changes with Z, or the flux F, lower or higher, lower or if higher. But do not take care of the convection and the latent heat. So it is found to be lapse rate is found to be unconditionally unstable in such models. Also, this equilibrium based radiative transfer models include the presence of different kind of gases, and this presence of different kind of gases has been taken care with their optical depth. Now, uh, so another thing, uh, our atmosphere radiative equilibrium model for the atmosphere has been discussed in our lecture. That is, and this model was assumed in three of this different case assumption, or the three of the different condition. The assumptions or the three conditions were maintained while building this radiative equilibrium model. So the first condition was the atmosphere is transparent to the shortwave radiation coming from the sun, and all the shortwave radiation that is not being reflected by the Earth's albedo alpha is being absorbed by the ground. No gas in the atmosphere absorb the shortwave radiation, and this shortwave radiation is absorbed by the ground, and this is re-emitted as the long wave radiation, or known as the long wave terrestrial radiation. For the atmosphere and the ground, the diffuse approximation was taken. That is, the radiation intensity is independent of the angular direction. That at the theta phi direction there has been no change of the emission. Only the change in the direction was in the z direction. And this gray approximation was considered. So by this gray approximation term, it is means that the mass extinction coefficient is independent of the frequency in the infrared range, and this gray approximation is applied when the frequency is greater than the visible frequency. Because we are in the infrared frequency, this gray approximation is valid. Now in this radiative equilibrium model, the ground temperature can be written as a function of the emission temperature, that is the emitted from the emission temperature, and the effective equivalent optical depth. So this formula has been discussed in our lecture. That is, the ground temperature is equals to emission temperature into some factor, which factors takes care of the optical depth of the ground, or the effective optical depth. And effective optical depth of ground is put in while computing the ground temperature. So this, from this formula, there is this 8 question has been given. So if the effective emission temperature, you know, that is 255 Kelvin, and the equivalent optical depth of ground is given 4 unit. So 4, then choose the closest answer. And you can see here the optical depth has no unit always. Choose the closest answer. What will be the ground temperature in this scenario?
Three 36.
Uh, 8, yes, 8 is 336. Yes, 335.6 or 336. And also we can just check these formulas that at the z direction above the ground, this equilibrium atmosphere model, we can have the this Tz is equals to Te into the factor Te into 1 plus tau z stirred by 2 to the power 0.25. And also we have this equation, sorry, this, so this is the at the ground. At the ground temperature, at the ground we can write this formula, and we can see that as tau g is greater than 1, so ground temperature is always higher than the effective temperature in this equilibrium atmosphere model, because this factor is always greater than 1, so Tg is greater than Te always. Now the question 8 is, which of the following gases contributes most to the long wave cooling of troposphere? Carbon dioxide, ozone, nitrogen and H2O. We had seen the cooling, this lapse rate curve for different kind of atmospheric species or atmospheric gas species. We saw that the H2O is the lower, so H2O mainly contributes to the cooling, long wave cooling in the troposphere. Now we can rediscuss about the heating and cooling of this different atmospheric layers. In the troposphere layer, heating is mainly done as the short wave radiation is get absorbed and get conduction and the convection from the ground. Water vapor and some gases can absorb a small fraction of short wave and long wave, driving the further heating, but this is not the very much plausible case. And this troposphere cooling is dominated by infrared radiation from the water vapor and carbon dioxide back to space, resulting the net cooling with altitude. In the stratosphere, cooling is mainly long wave emission by the carbon dioxide facilitates net radiative cooling despite UV heating, especially at the upper levels. So in the mesosphere and the thermosphere also there is a heating and cooling effect, but for shaping the atmospheric heat circulation, this has low, it has not direct impact. Now the question 10. The vertical temperature profile of the atmosphere under the radiative equilibrium model will lack of which feature if ozone is not considered in it? The turning of temperature profile above stratosphere, the linear decrease of temperature profile in troposphere, the unconditionally unstable nature of temperature profile, matching the temperature of atmosphere at the ground. In vertical temperature profile of atmosphere, under the radiative equilibrium model, will lack of which feature if ozone gas is not considered within it? The turning of temperature profile above stratosphere, the linear decrease of
Option A.
temperature profile in troposphere, the unconditionally unstable nature of temperature profile, and matching the temperature of atmosphere at the ground. Yes, question 10 option A is correct. This turning of temperature profile above the stratosphere cannot be described without adding ozone in this radiative equilibrium model. Question 10 option A is correct. Question 11. The high radiative lapse rate makes the atmosphere unstable. Hence, it causes the development of large-scale vertical convective currents that transport additional heat from the lower to the upper troposphere, and thus causing lowering of temperature lapse rate. Is this statement true or false? The high radiative lapse rate, that is a high radiative lapse rate, makes the atmosphere unstable. Hence, the large-scale vertical convective currents are developed, and this large-scale convective current transport additional heat from the lower to upper troposphere, thus lowering the temperature lapse rate.
No idea.
Uh, we have to, I guess, this statement is true, but today I have not written about this high radiative lapse rate and the temperature lapse rate description. I will discuss the main key thing about this question in the next day, I guess. But this statement is question 11. This statement is true. I will discuss this question 11's this two key thing, that is the temperature lapse rate and the radiative lapse rate in the later class, and the adiabatic lapse rate in the later class. So there are three lapse rate we are getting. So we have to compare those. Now question 12. Which of the factors don't contribute to the net upward long wave radiation? Spectral transmittance, spectral blackbody radiation intensity, atmospheric temperature, and all of this contribute. Which factors do not contribute to the net upward long wave radiation?
Atmospheric temperature.
I guess this question is directly from sorry, from this week 6 content, where they have put that net upward flux is a function of this tau g f0 z hi, net upward flux at the z position. So here the net upward long wave radiation, there is has been dependence on the spectral transmittance tau, and also black body radiation intensity b at tz, there is also this dependence, and atmospheric temperature dependence, that is coming from the directly from the tz. And this model they have been starting, we are starting with also. So these two equations are written, that is how this upward flux changes, that has a dependence on this Planck function, you can see. Also this downward flux, how the downward flux changes or changes, that has dependence on this Planck function. So from this two function itself, it is evident that all these three factors, that is Tz, this black body intensity, B at Tz, and also spectral transmittance, which is included into optical depth, both three contribute in this F.
But in the
Upper.
question, we have to write which is not contributing.
Yes, which do not contribute to upward long wave radiation. Uh, which do not contribute. All of them contribute, of course. Oh, sorry. All this contribute. Yes. I guess for MCQ optical, this option D is correct. Do not contribute, but all this contribute. Only option D is only given, all of them contribute.
But D is true, and they are asking for which is false. That means
Yes.
do not contribute, but all of them are contributing. So this will create confusion at the
Yes.
final exam.
Yes, the question is itself very confusing, but they were giving this answer option D correct. This were the previous year question, previous year weekly question, so they were giving option D correct. All these factors contribute, we can see from the equations. Now question, yes, this kind of questions will be confusing some sense. In question 13, under the radiative equilibrium model, the ground temperature, that is Tg, and the air temperature just above the ground are same.
False.
Yes, this comes from this equation, that ground temperature is equals to Te into 1 plus tau g by 2 to the power 1 by 4. Now the air temperature is just above the ground is Te, that is emission temperature. So this emission temperature, so this Tg is higher than Te, always. They are not same.
It's
Yes.
T is not emission temperature. It's black body temperature. Black body emission temperature.
Yes, this is T.
Of the atmosphere.
Yes,
At the top of the atmosphere.
T is the black body temperature. Yes, and the air temperature, you can write this formula, rewrite this formula for the air temperature also. Yes. And this at the lower atmosphere temperature, there is a dependence of the Te, have dependence on this lower atmosphere temperature. Is not it? But they are not same. Question 13. Now we will go to the question 14. Which at we need to write this equation of this equation. Now question 14. At which optical depth just a heating rate minimizes? 1 to 0.53.
3.
Is it at which optical depth hitting that minimizes? Yes, this is 3. Now the question 15. The Coriolis force occurs mainly due to conservation of angular momentum of Earth's rotation and this pressure gradient. This statement is true or false? The Coriolis force occurs due to conservation of angular momentum and the Earth's angular momentum which is generated from the Earth's rotation and the pressure gradient. This statement is true or false?
Now, can we explain the Coriolis force, effect of Coriolis force?
Effect of Coriolis force. So, in this lecture itself, it has been explained. Uh, okay. We will do this Coriolis expression, derivation of Coriolis force in the later class, I guess. I don't have any much, very much image based knowledge for this Coriolis force derivation now. I will try to describe this Coriolis force in the next class. Is it okay?
Okay.
Okay. And this Coriolis force is mainly developed due to the conservation of angular momentum, or only developed for the conservation of angular momentum. It have no uh, dependence on the pressure gradient. So this statement, question 15, is false. Now the question 16. In the Gray approximation that were used for the radiative equilibrium derivation, the temperature distribution in the continuously stratified atmosphere, it was used, and it is applicable for what range of wavelength? We know it is applicable for the infrared spectrum. Wavelength greater than 0.4 micron, wavelength greater than 0.7 micron, wavelength greater than 14 micron, or wavelength lesser than 10 micron, it is applied.
Option C.
Yes, the Gray approximation is applied when there is infrared, that is greater than 14 micrometer. Greater than 8 micrometer it is not applied because Earth's backbody radiation peaks at 10 micrometer, and H2O base absorption is present in that 10 micrometer region. So for this question 16, option C is correct. Wavelength greater than 14 micrometer. This Gray approximation is correct, and Gray approximation means the absorption coefficient that is independent of frequency. Now question 17. The heating rate of is non-uniform throughout the vertical extent of atmosphere. This question is true or false? If you assume a vertical column of atmosphere, the heating rate, that is Q,
True.
yes, Q dot is a function of Z always. This statement is true because there is temperature dt dz is written by function that dt dz is written as a function of qz, that is heating rate, by rho cp. and this qz is also a function of the how the flux, the long wave flux varies from the from low to high atmosphere. So absorption and the as absorption and emission vary with the height due to changing pressure, density and composition, heating rate is not a constant factor with the increasing z. So this question is correct. This is non-uniform heating rate from a column of atmosphere. This is true. Now the question 18. Uh, Given the angular velocity of the earth is 7.29 into 10 to the power minus 5 power minus 5 radian per second, calculate the Coriolis parameter at the latitude of 25 degree north. Given the angular velocity of earth is 2.79 into 10 to the power minus 5, find the Coriolis parameter at latitude 50 degree north. We have not discussed the Coriolis effect derivation in earth. So this Coriolis, today we will cover only the math part. So the definition I will tell you to derive from the definition itself. That is 2 omega sine phi is the f or the Coriolis parameter. What is the Coriolis 18? What will be the Coriolis parameter at latitude of 45 degree? Coriolis parameter is defined by f is equals to 2 omega sine phi. If you do not have calculator, then sine phi is 1 by root 2 into given the angular parameter of the earth, calculate the Coriolis parameter at the latitude 45 degree north. So this Coriolis parameter equation is 2 omega sine phi. This is coming to be about 10 to the power 1.03 into 10 to the power minus 4. This Coriolis parameter, none of these options are correct. There was a yes. This was 10 to the power minus 4, I guess. Question 19. The cyclonic winds in the southern hemisphere rotate in which direction? We will derive this direction due to the Coriolis force in later class. But it is the thing that when when there is a air, suppose this is Earth, due to Coriolis force, if any air that moves in the northern direction from this region to this, that or any vector or the direction of air, this air will move to the direction of right of its in the right of its going direction. And if it travels from this equilibrium, this 0 degree latitude to polar region, then it moves to its left. So its left is this direction. And from this, and also this cyclones are when there is a low pressure system in the inner region, there is high pressure system in the outer region, then it is called a cyclone. And this cyclone can generate in any of this hemisphere, northern hemisphere or southern hemisphere. Now this question is, cyclonic winds in the southern hemisphere rotate in which direction? Therefore, for this southern hemisphere, if this travels this direction, then it will move leftward. So all the air vectors goes like this will this. Therefore, cyclonic winds in the southern hemisphere rotate in southern direction, clockwise direction. So here you can see this thing more clearly. In the cyclone is when there is the low air pressure in the center and high lower pressure in the outer region. So if this high pressure to low pressure, so air packet will try to go from the outer to inner region, and this air packet will shift to this right of this thing. So there will be an anti-clockwise flow of this air in the northern hemisphere cyclone. But for the southern hemisphere cyclone, when the air try to move this direction, it will move this way. Left of it will move. So it will have the clockwise motion of the air when this has been seen from the upward view. So in the northern hemisphere, air flows from the storm's center from the all direction, but it is deflected towards the right of its going direction. So it makes the tropical cyclone in the northern hemisphere to rotate the counterclockwise. In southern hemisphere, air is deflected towards the left of its going direction. So this air packet will move in the tropical cyclone in the clockwise direction. Without Coriolis effect, airflow would be straight towards the storm center, and the tropical cyclone would not rotate without this Coriolis force. So for this question 19, option A is correct for the cyclonic wind of the southern hemisphere. Now question 20. If density of air is given to be 2 kg per meter cube, and the gravitational acceleration has been given to 9.8 meter per second square, what will be the vertical pressure gradient in the state of hydrostatic balance? If the air density is 2 kg per meter cube and the gravitational acceleration is 9.8 meter per second square, what will be the vertical pressure gradient in the state of the hydrostatic balance?
Which equation we have to use for this?
So for the question 20, for the hydrostatic balance equation is when dp dz is equals to minus rho z.
Okay.
This is 20. Change in pressure is related to the gravity. Hydrostatic balance means question 20, I guess. Yes, 19.6. This is correct. Yes. And the unit will be Pascal meter cube. Sorry, Pascal per meter. Sorry, Pascal per meter. Pascal is the unit of pressure, and by Z, that is the inverse meter. In the question 21, due to Coriolis force, south moving widths in the southern hemisphere inclines to the west. We had seen that, yes, in the south going winds means this wind direction, and it will move towards its left of its moving direction, so it will move towards the east. This statement in this question is false. So this, in the southern hemisphere, the Coriolis deflection is to the left of its motion direction. If a parcel of air moves south, the left of the south is east. So this southward moving parcel will deflected to the eastward direction, not the westward direction. Coriolis force describes the way how the Earth's rotation causes movement of the air and the wind to curve. Instead of traveling in the straight line, the air packet is deflected due to this Coriolis effect, and this in the northern hemisphere this effect is rightward the motion, and the southern hemisphere this effect is leftward the motion. Now in the question 22, this is the same kind of question, I guess. Suppose there is an air parcel which has the mass of 5 into 10 to the power 6 kg in the troposphere. The specific heat capacity at the constant pressure is 1004 joule per kg per Kelvin, and the temperature increase is at the rate of 0.01 Kelvin per second. Then the total heat per added per second is in unit of what? Megawatt. Suppose air parcel has the mass of 5 into 10 to the power 6 kg in the troposphere. The specific heat capacity at the constant pressure, that is the Cp, has been given the value 1004 joule per kg per Kelvin, and the temperature increases at the rate of 0.01 Kelvin. Then the total heat added per second is dash megawatt. Now this question will be coming from this equation. Here the mass of the air parcel has been given and the specific heat at the constant pressure has been given. Also per temperature increase has been given for the per unit second. Now this Q dot is equals to mCp into dt by dt, capital dt by dt. So this can be, you can calculate. M is 5 into 10 to the power 6. Cp is 1004. Yes, this is 50.2 megawatt. Now the question. Question 23. The long wave volumetric heating rate is always positive, means that rate is usually positive, meaning there is net heating. If the volumetric heating rate is positive, then
True.
yes, this is 23 is true, false. Whether this question has been given answer false, because the long wave volumetric heating rate, positive or negative, it depends on the layer. Many atmospheric layers do not lose net long wave energy as they emit in the space. The surface typically gains or absorbs long wave or the atmospheric layer. So it is not generally true that long wave volumetric heating rate is usually positive. Often it represents the net effective cooling of the atmosphere. Question 23 false.
Positive heat, positive heating rate, how it cools?
I am not very sure about this question. I guess I have to rediscuss this question later, I guess. 23 I am living today. There are some questions I have to live today. Sorry for that. Question 23. Long wave volumetric heating rate is equals to, we know this function, that is the volumetric heating rate is equals to minus del F del Z. Usually positive, meaning there is net heating. I have to rethink this question again. Question 23 I am living.
Okay.
Okay. Question 25. This is another Coriolis effect question which we will solve just by the mathematical equation. So in this question it is given that at the latitude of 45 degree north, where the sine 45 is 0.7, the zonal wind speed has been given to be u is equals to 20 meter per second in the eastward direction, and the meridional wind speed, that is the south to north wind speed, that is given to be v is equals to 0 meter per second. Taking the Coriolis parameter function, that is 2 omega sine phi, where omega has been value of 7.23 into 10 to the power minus 5 radian per second. What will be the meridional component of the Coriolis force per unit mass based on the expression, where Coriolis force per unit mass has been written in the written as the function as the or the, as f into v I cap minus u j cap, where I cap is the unit vector towards the eastward direction and j cap is the unit vector towards the northward direction. Eastward, westward. At the latitude of 45° north, where sine 45 has been given and the zonal wind speed are given as the in the eastward direction, the speed is 20 meter per second, and this south to north direction or the meridional direction, this is v is given 0 meter per second. So the net velocity is towards the direction west to east. Taking the Coriolis parameter as the 2 omega sine phi, what is the meridional component of the Coriolis force per unit mass based on the expression, where the Coriolis force per unit mass has been given by F V I cap minus U J cap. Always the meridional component, that is the south to north component or the J cap component. This J cap component only have effect here. You can see this is the J component, this is I component, this is I, this here there is velocity. So this meridional only the meridional component survives here because V is equals to 0 itself. So Coriolis force per unit mass has been always in this question is always in the direction from the south to north meridional plane. So what will be the 2 omega sine phi minus u j cap?
How to calculate that?
Uh, so here in this question, Coriolis force per unit mass is given in this equation. So here this equation is F is equals to F into Coriolis force per unit mass is given as V I cap minus U j cap. Here in this question it is given that U is equals to 0. U j cap. V is equals to 0. So there is no force in the I direction. You can cancel this. So this is minus F U j cap. What will be this value? Coriolis force per unit mass. It is itself in the meridional direction. You can see this is j cap is south to north. for this question, so Coriolis force per unit mass has been written in the function of 2 omega sine phi into V I cap minus U j cap. In this question, V is 0 itself. There is no meridional component. Only, there is no zonal component. Only the meridional component survive. So here the would be root 2 into uh, 7.29 into 20. So this is coming around root 2 into 7.29 into 20 into 10 to the power minus 5. 2 into 10 to the power minus 3. Yes, 2 into 10 to the power minus 3. Now question 26. Anticyclonic winds have low pressure in the center surrounded by hot pressure zones. High pressure zones. Anticyclonic winds have low pressure in the center surrounded by the high pressure zones. This statement is true or false? For the cyclone case, we have seen there is a low pressure and a low pressure inside and a high pressure outside. But for the cyclone, this is cyclone. Anticyclone is the opposite. High pressure center, low pressure outward. So this question 26 is false. Yes. Therefore, you can see this. A cyclone is a large air mass that rotates around a strong center of low atmospheric pressure. This cyclonic air movement is counterclockwise in northern hemisphere and clockwise in the southern hemisphere. Cyclones are associated with the wet and stormy weather condition. An anticyclone is a large air mass that rotates around a strong center of high atmospheric pressure, counterclockwise in the southern hemisphere and clockwise in the northern hemisphere. Anticyclones are associated with the dry and the fair weather conditions. Cyclones are named due to their circulation direction. Cyclones and anticyclones have reverse uh, movement direction. You can see in this previous plot. Here we have seen. Here in the northern hemisphere, cyclones move anti-clockwise, but anticyclones move clockwise. In the southern hemisphere, this effect reverse or flips. This anticyclones now moves counterclockwise and the cyclones move the clockwise direction in the southern hemisphere. Now for the question 26, this was false. Question 26 and then in the question week 7 contain the global atmospheric circulation model was discussed. So this global atmospheric circulation is the movement of air within our planet. It explains how thermal energy and the storm systems move over Earth's surface. Without Earth's rotation or its tilt relative to Sun at the 23.5 degree or the surface water, global circulation would be simple. With the Sun directly at the equator, the ground and atmosphere there has been heat up more than the rest of the planet. This region would become very hot with hot air rising into the upper atmosphere. This would create a constant belt of low pressure system around the equator always. This warm air then move that warm air then move directly towards north, towards the south pole, where it would become cold and sink, create a large area of high pressure. The temperature and the pressure difference would return the now cold air south to the equator above, right, creating the simple global circulation model. However, the Earth's tilt means Sun is not always directly overhead the equator. Thus, the exact location where the most solar radiation has been falling is constantly shifting. The Earth's rotation results the easterly movement of the air in the known as the Coriolis effect. The uneven distribution of water and the land around the globe further breaks the uniformity of the air movement. With the large amount of land in the northern hemisphere create a semi-permanent or highs and lows. As a result, the actual global pattern of atmospheric circulation becomes more complicated between the different latitude. Instead of one large circulation in each hemisphere, there are three circulation cells you can see. Here some air moves up, that those come down to here. Here from there some moves up, comes down, moves up, come down, moves up, come down. This three kind of shells has been discussed in the week 7 content. The first cell is the Hartley cell, then is the Ferrel cell, then is the polar cell. The Hartley cell at the lower latitude, air moves towards the equator where it is heated and raised vertically. In the upper atmosphere, air moves poleward. This forms the convection cells that covers tropical and the subtropical climates. This Hartley cell was first proposed by the meteorologist George Hartley in 1735, and that time when this first Hartley cell was proposed, it was believed that there was no other Ferrel or polar cell. Each of the hemisphere has a single cell, but this is incorrect. Now the Ferrel cell, in the mid latitude, atmospheric circulation cell, air near the surface falls poleward and eastward, while the air in the higher atmosphere moves equatorward and the westward. This was proposed in the by William Ferrel in 1856. Was first account for westerly winds in between 35 degree to 60 degree northern or southern latitude, northern and southern latitude, which causes by the friction, not heat differences at the equator and the poles. The polar cells at the high latitude cell, air rises and travels towards the pole. Once over the pole, the air sinks and forming areas of high atmospheric pressure called the polar high. At the surface, air moves outward from the polar high, creating the east blowing surface wind called the polar slides. This is the smallest and the weakest of among all the other cells. This cells describes the circulation of wind in the northern and the southern hemisphere. Although the difference in the land mass in the result am I audible? I guess I was disconnected.
Yes, ma'am.
Okay. Uh, so these three cells had lesser. Yes.
It's presentation is not clear. Now it is clear.
Is it visible now?
Yes, ma'am. Now it's okay.
Yes, this Hadley cell, Ferrel cell, and the polar cells in the both northern and the southern hemisphere describes the how the wind flows. Between each of the circulation cells, there are surface level bands of high and the low pressure. The high pressure band is located about 30 degree north or south latitude and at each pole. The low pressure bands are found at the equator and the 50 to 60 degree north or south. Usually, the fair and dry hot weather is associated with high pressure, while rainy and the stormy weather is been associated with a low pressure zone. You can see this results of this circulation on a globe. Here in the Earth's map, you can see there are more deserts are located near the 30-degree north southern region. Then between 50 to 60-degree northern and southern latitude, there are there is also desert regions. This latitude, especially on the west coast of the continents, tend to have more precipitation due to storms moving around the earth. We will discuss this uh, last paragraph in later, but for now we have seen three kind of cell: hardless cell, feral cell, and the polar cell. Now there will be few questions regarding this cell atmospheric circulation of earth. Question 27: Hartley circulation occurs in which of the layer? Tropics of the stratosphere, equator of troposphere, tropics of the troposphere, uh, equator of stratosphere.
Option B.
Question 27, equator of question 27. The Hadley cell do not extend it to the stratosphere itself. It has been seen to the tropical option B you are saying. Tropics. This is, I guess, this is tropics of the troposphere will be this, because 0 to 30 degree we are going, not in the equator region. Equator is 0 to 10 degree or that latitude is always. Question 27 is option C correct.
Okay.
Question 28 is which of the following, so this tropics is the Tropic of Cancer, this two zones, 23 degree north, 23 minus 23 minus degree south, those things are covered in this Hadley circulation. So this option C is more correct to me. Question 28: Which of the following forces are considered to be apparent or the pseudo force arising from the Earth's rotation?
Coriolis force.
Yes, Coriolis force is the apparent force which is dependent on the frame of reference. In the rotating frame of reference, this Coriolis force acts, and as our Earth is rotating, so if we want to visualize how the wind moves from our rotating system, then we have to add this Coriolis forces effect.
What is frictional force here?
The frictional force, I guess this frictional force was this, what are they calling frictional force? Did they mentioned? I have not seen. Yes, they have mentioned that their frictional force is the force due to the ground surface. Presence of friction reduces the wind speed due to frictional drag effect. It in this is in turn reduces the Coriolis effect as it is proportional to the wind speed. This makes the pressure gradient forces stronger. Yes.
Friction means there must be two surfaces. So in between.
Not this is air friction, I guess. They are discussing here air friction.
That means between two air layer or air and ground. Between air and ground.
They are giving it air and ground, I guess. Here the frictional force. And also between two air surface there must be some forces. Yes, these two kind of forces are frictional force, ground air or air layers. These two fall in the frictional force category. Now for the question, is it okay? Yes. Hello.
Yes, ma'am.
Okay.
Yes, yes.
Yes. So now there is another concept of the thermally direct circulation and thermally indirect circulation here, where this Hartley cell and the polar cells are called to be thermally indirect circulation, whereas the ferrule cell, that is from the 30 degree to 60 degree northern latitude or the southern latitude, that is called the thermally indirect circulation. This thermally direct or thermally indirect atmospheric circulation at the distinct pattern by which air moves in the atmosphere and governed by the relationship between temperature and the vertical motion. Thermally direct motion or the thermally direct circulation occur when warm air rises and the cool air sinks, while the thermally indirect circulation features the opposite. Here the cool air rises and the warm air sinks. So this thermally direct circulation is often driven by is mainly driven by the difference in heating. So in the Hartley cell you can see there is the warm air rises and the cool air sinks, while thermally indirect circulation, this here the cool air rises and the warm air sinks. Thermally direct circulation is driven by the difference in heating, with the warm air rising and the cool air sinking, directly converting the thermal energy into the kinetic energy. For the Hartley cell and the polar cell, this thermally direct circulation happens. Air rises in the warmer regions, moves aloft, then cools and sinks in the colder areas. You can see here the air rises from the equator, moves aloft and cools, and then sinks in the colder areas in the subtropics. And in the thermally direct in the thermally direct polar cell, here the warm air rises, moves aloft, and it sinks. This process helps to redistribute heat from the warmer air to the cooler air across the globe, maintaining the thermal balance in the atmosphere. But for the ferrule cell, which occurs from the 30 degree to 60 degree this latitude region, the main idea is different. Here the cool air rises, here the cool air rises and warm air sinks. Here cool air rises and the warm air sinks. You can see the cool air at the 60 degree latitude, that is rising, and then the warmer air here is sinking, meaning that the energy must be supplied through some mechanical means such as atmospheric wave rather than the pure temperature induced density difference. It is a classic example of the ferrule cell in the mid latitude between 30 degree to 60 degree latitude, northern or south. Despite of the warmer temperature at the surface, air sinks and despite of warmer temperature at the surface, air sinks and cool air aloft rises, opposing the direction expected from the heating alone. Therefore, for this thermally direct circulation and thermally indirect circulation, thermally direct circulation, warm air rises, and cold air sinks, while thermally indirect circulation, there is the cold air rises but the warm air is sinking. Now question 29. This is also on the concept of atmospheric circulation. That is 29 is the surface winds are not in the geostropic balance. This statement is true or false? Surface winds are not in the
True.
geostropic balance.
True.
Question 29. Surface winds are not in geostropic balance. Yes, this is uh, yes, this is true. Question 30. The Hadley circulation is characterized by which of the following feature? Rising air near equator, sinking of air near 30-degree latitude, surface wind flowing poleward from equator. It is thermally direct circulation.
Option D. It is thermally direct circulation.
The Hadley cell is surface winds is flowing poleward from the equator. Question 30, option C is
Oh,
correct,
no,
I guess.
Hartley is indirect circulation.
Hadley is the direct circulation, thermally direct circulation. Here the air is
Then option D is correct.
Hadley circulation is characterized by which of the following features? Rising airs near equator, this is true. Sinking of air near 30-degree latitude, this is true also. You can see equator air rising at 30-degree latitude, it is sinking. Surface winds flowing poleward from the equator, this is not true. Equator, surface wind, pole to equator, there is surface wind. It is a thermally direct circulation. Option C is also true. True. So there three are true.
Okay.
Yes. If there was which is not correct, then option C will be correct, but it is a MOQ. Three are correct. Question 31. The geostropic wind is a result of balance between which of the two forces? Coriolis forces and frictional force, pressure gradient force and the gravitational force, Coriolis force and the pressure gradient force, frictional force which is due to the air and the earth surface, and the gravitational force. I guess here frictional force means they are giving the air and the surface force only. The geostropic wind is a result of balance between which of the two forces? Coriolis force and the frictional force, Coriolis force and the pressure gradient force, pressure gradient force and the gravitational force and the frictional force. Question 31. Option C is correct. Geostropic wind is a result of balance between Coriolis force and the pressure gradient force. In the free atmosphere above the surface, wind flows parallel to isobursts because the Coriolis forces get balanced by the horizontal pressure gradient force. Gravity is balanced vertically by the hydrostatic balance. The geostropic balance is the balance between Coriolis force and the pressure gradient force. Coriolis force parameter into the Vg, Coriolis force parameter into and the pressure force. This can be written as a function of Fvg is equals to 1 by rho into del P del x, and Fug is equals to minus 1 by rho del p del y. So here also for the Lord spatial scales away from the surface, so the frictional force effect has been small, and far from the equator where the Coriolis force are weak, because sine phi is where the Coriolis force are weak, the only horizontal force of importance that drives the parcel of air are the horizontal pressure gradient force and the Coriolis force. When the two forces balance each other, the resultant flow is said to be the geostropic balance. The corresponding force, this corresponding velocity which is got by the air parcel is called the geostropic velocity. So this question, the geostropic wind comes from the balance of the Coriolis force and the pressure gradient force. Now the question 32. What are the surface level winds called that blow from the subtropical high pressure zones towards the equatorial low pressure zones in the northern hemisphere? What are the surface level wind that is blow from the subtropical high pressure zones to the equatorial low pressure zones is called in the northern hemisphere? Mid latitude west layers, polar islets, southeast trade winds, northeast trade winds. At the surface, from the subtropic high pressure zones to equatorial low pressure zones, some wind is blown, and in the northern hemisphere it has name. It has some particular name. What is that?
Option C.
Is it? This is known as from the subtropical zone to the equatorial low pressure zones. Here is the surface wind pattern has been shown. Here when this wind is blowing, it is moving to the right of its direction. So if this moves, this will go right. It is known northeast trade winds. This is the surface wind profile. This is known as northeast trade winds in northern hemisphere. This is this Hadley cell's surface component, you can see. Northeast trade winds. Question 32, option D is correct. This is the Hadley cells, this is the low component, ground component, surface component of Hadley. Now the question 33. Feral cell occurs at tropics. This question is true. This statement is true or false?
True.
Yes, this is false. This feral cells, you can see this feral cells is here 30 to 60 degree, not in the tropical region. So question 33 is false. Question 34. The Coriolis force, for the large scale atmospheric motion, the Coriolis force has been written. Yes.
33 false or true?
This is false, because feral cell is HP 30 degree to 60 degree. Okay, this is subtropic. Is not it? This is subtropic.
Subtropic. Okay.
Yes, subtropic. Subtropic or mid latitude. Yes. Question 34. The Coriolis force for large scale atmospheric motion, it depends on the which of the following: air density, latitude, zonal component of the wind velocity, the meridional component of the wind velocity. The Coriolis force has been defined to be Coriolis force per unit mass is equals to Coriolis force per unit mass has been defined to be F into Vi cap minus U J cap. I is the west to east direction known as the zonal velocity direction or the zonal direction, and this south to north, this direction is known as the meridional direction. Now this F Coriolis depend on which of the following parameter, and F is the
All of them.
two,
All of them.
but air densities does not depend. F is only 2 omega
Once
sine
mass
phi.
is depend on density, and they are asking for Coriolis force, not Coriolis force per unit mass.
Yes. Coriolis force. Yes, all of this have dependence. So option A, B, C, D is correct. For the only for Coriolis force per unit mass, there will be no dependence on the air density. So thank you. Question 34 is option. All the options are correct. Now question 35. Which of the following forces does not drive atmospheric wind circulation? Coriolis force, pressure gradient force, frictional force, gravitational force, and the magnetic force.
Magnetic force.
Yes, magnetic force has no effect in the atmospheric circulation. Atmospheric wind circulation is driven by the only these four forces: Coriolis force, which affects from the rotation of the earth; pressure gradient force, as the air density is changing with the temperature, the altitude; and the frictional force, yes, there is a frictional force between ground and air, also between different air layers. And the gravitational force is balanced for the for the vertical extent, and this magnetic force has no effect in the atmospheric wind circulation. And then question 36. What is the angular speed of Earth's rotation?
Option C, 7.29 × 10⁻⁵.
Yes. Option C is correct for the question 36. Now question 37. At which latitude the Coriolis force is 0? The Coriolis force factor is equals to 2 omega sine phi.
0 degree.
Yes. This is Coriolis force is 0 at the equator. At the pole it is maximum. Now in question 38, during northern hemisphere summer, that is within the July month, this intertropical convergence zone lies around what latitude?
What is the full form of ITCJ?
Intertropical convergence zone. It was discussed in the week 7 content only. and this ICTZ. We will discuss this ICTZ kind of thing in the next class. This intertropical convergence zones where these two surface layers merge. That is these two surface layers merge in this region from the northeastern trade wind and the southeastern trade winds. These two merge in some layer, but where this will merge will depend on the where this sun rays are falling or what is the inclination axis of the earth. So this ICTS is known to be shift with the northern hemisphere summer, northern hemisphere winter. That time that oscillation is ICTS is seen during northern hemisphere summer. The ICTZ is seen around the 20 degree to 10 degree this latitude, not just above in the 0 degree. Now next is the 39. Which type of wind circulation is been between 30 degree north and the 30 degree south?
Headless.
Yes, this is Herdlesser within 30 degree north to 30 degree south. Now question 40. An originally not moving wind in the northern hemisphere will get tilted to the northwestern direction. An originally north moving wind in the northern hemisphere will be tilted around northwestern direction. Similarly, we can show south moving wind will be tilted towards the southeastern direction. This statement is true or false? This statement is false. The second part is also only true, but in the northern hemisphere north moving, it will shift towards right, so it is northeast direction it will move. So this whole statement becomes false. Now question 41. The formula for the Coriolis parameter is given by which of the following?
Option B.
Yes, this is option B. And question 42. The pressure gradient force always moves air from the high pressure to the low pressure. This statement is true or false?
True.
Yes. Question 42 is true. Now question 43. What are the primary surface level winds in the mid latitude, that is 30 degree to 60 degree latitude, both in the southern hemisphere and the northern hemisphere? Polar islands, mid latitude west layers, trade winds, subtropical islands.
It is subtropical region, so maybe subtropical.
In 30 degree to 60 degree, 30 degree to 60 degree we can 30 degree to 60 degree, it is called the mid latitude west layers, subtropical, because from the west direction it is flowing in the surface. You can see this is the ferrule components surface ferrule cell surface component. This is the ferrule cell surface component. Ferrule cell surface component. Ferrule cell surface component. Then So in the mid latitude, it is ferrule cell surface component. Then from the northern hemisphere, it is this is ferrule cells surface component. This is ferrule cell surface component. So it is moving from the high pressure to low pressure region. You can, it is moving northern hemisphere, it is moving upward. 30-degree north to 60-degree north. So moving towards east, then originated towards west. Known as mid latitude as west layers, westerlies. So the primary surface level winds in the mid latitude is the polar westerlies, mid latitude westerlies, trade winds, and the subtropical easterlies. So the surface level winds are the component of the ferrule cell. You have seen that three types of cell: Hadley cell, ferrule cell, and the polar cell. At the Hadley cell, it was seen 0 to this direction was wind flow. This was Hadley cell. But the ferrule cell, you saw this kind of wind flow. This is ferrule cell. So in northern hemisphere, it will go from low to high. That is, in the northern hemisphere, this will go this direction, but it will bend towards its right. So this is known as the westerlies. Then question 44. The ferrule cell is described as strong and thermally direct, weak and thermally indirect, strong and thermally indirect, and weak and thermally direct. We saw ferrule cell. Here the cold air moves up and the high air sinks down, and it is a thermally indirect flow. And question 44. This is called to be weak and thermally indirect. Question 44, option B is correct. Question 45.
Why weak, man? Why it is weak?
This weak strong, I am not very much clear, but I guess weak strong is depending on the velocity. This weak strong, I am not very much clear. I have to be clear out. Sorry for that. Maybe that is due to velocity, but velocity gain thing we have to check. Question 45, I guess I should. Question 45 and question 46. Sorry, question 45 to question 50 I am skipping. 45 to question 50 I am skipping. Now question 51. We will describe 51 to 60 today. In the week 7 content, in Coriolis force derivation, the zonal momentum equation was described with the Newton's second law. This was done to derived by applying Newton's second law. And why this was done so, and in which frame it was done: a non-rotating earth frame, a rotating earth in inertial frame, a rotating earth in non-inertial frame, a frictionless fluid only.
Option C.
Yes, this is rotating earth, non-inertial frame. The derivation was done. The total derivative, the ddt, was written. It represented the local time changes only, motion relative to ground, rate of change of following a moving air parcel, and D is the hydrostatic balance equation.
Option C.
Yes, the total derivative was done to get the estimation of the rate of change within the frame of a moving air parcel. Or the rate of change following a moving air parcel. Question 53. The vertical Coriolis force is neglected here because it is identically zero. Gravity is much stronger in vertical direction. Pressure gradient dominates vertically. Latitude dependence vanishes.
Option D.
This is question 53. The vertical force were neglected. They were, the gravity is much stronger than in the vertical direction, so the vertical force were neglected. Question 53, option B is correct. Question 54. The Coriolis parameter for very small phi is written at by what?
Option D. D.
Yes, this is option D. Sin phi is equals to phi approximation. Coriolis reflection is minimum at which of the latitude? 0 degree latitude, 30 degree latitude, 45 degree latitude, and the 90 degree latitude. Yes, this is a sin phi is 0. Now question 56. Which force dominates in the vertical direction? Pressure gradient force, Coriolis force, frictional force, and the gravitational force.
Gravitational force.
Yes, 56. Gravitational force dominates in vertical direction. This 57, I do not have equation. 57 I am living. 57 you can check from the note itself. Now this I would not discuss today, I guess. This was the 56 was today's last question. Today I cannot describe few of the question, and I quit few of the questions which I have to rediscuss in the next class. So here I am stopping presentation.
Okay, ma'am. Thank you, ma'am.
Yes.
For the presentation.
Any other question or any other comments for discussion?
No, ma'am. It's very fine.
Okay. Then
Okay.
thank you from joining. For joining. Yes. Thank you.
Okay. Bye.